Welcome to the week 2 problems. So let us begin with a quote by Richard P. Feynman. He says that I was a normal person who just did one thing, that is study hard. So let this be a motivational message for all to work towards clearing CSIL. So today's first problem is the solution of the differential equation dx by dt equal to 2 into root of 1 minus x square with initial condition x is equal to 0 at t is equal to 0 is. So there are 4 choices given. Now thinking about the answer, you should note a very important thing. A good method to think of a solution to the differential equation is to consider the solution as a key to open the door, that is the differential equation. We have dx by dt equal to 2 into root of 1 minus x square. So dx by root of 1 minus x square is equal to 2 dt. Integrating, you will get sine inverse x equal to 2t plus c. And here we should note that the modulus of x should be less than 1. Otherwise, the root of 1 minus x square becomes a imaginary value. So x is equal to sine 2t plus. Now let us put the initial conditions. At t is equal to 0, x is equal to 0. So the constant is 0. Now taking modulus on both sides, modulus of x, that is modulus of sine 2t should be less than 1. So 2t should be less than pi by 2. So t should be less than 1 pi by 4. So x is equal to sine 2t for t less than pi by 4 helps us to think that the solution may be 2 from the 4 available solutions. Now when we put t is equal to pi by 4, the answer for x becomes 1. So this should be also valid, and this condition is only satisfied by choice C. Now coming to problem number 2. A particle moves in 3-dimensional space in a center potential V equal to kr square. Kr raised to 4, where k is a constant. The angular frequency omega for a circular orbit depends on its radius r as, so there are 4 choices: omega proportional to r, omega proportional to r raised to minus 1, omega proportional to r raised to 1 by 4, omega proportional to r raised to minus 2 by 3. Now let us use the Lagrangian method to solve this problem. We know that L equal to T minus V. So T is half mv square, which is due to the kinetic energy in translation, and half mr square theta dot square, the half is missing there, that is due to the rotational kinetic energy. Now potential energy is k r raised to 4. So Lagrange's equation of motion becomes d by dt of dou L by dou r dot minus dou L by dou r equal to 0. So dou L by dou r dot equal to m, and dou L by dou r equal to minus 4 kr cube if we neglect the rotational kinetic energy. Let us say that it has only translational kinetic energy. So mr double dot plus 4 kr square into r equal to 0. So r double dot plus 4 kr square by m into r equal to 0. So this equation is a simple harmonic differential equation of the form x double dot plus omega square x is equal to 0. So omega square equal to 4 kr square by m, and omega is equal to 2 into root of k by m into r. So omega is proportional to R. That's the answer. Now problem number 3. Two masses m each are placed at a distance in the points xy is equal to a and minus a minus a. Two masses 2m each are placed at the points a minus a and minus a. The principal moment of inertia of the system R, that is Ix and Iy, R. The right answer is B, that is 4ma square and 8ma square. So let's first of all visualize this problem by drawing a cartoon. So you can see m placed at a and another m placed at minus a, while you can see two masses 2m placed at minus a and a minus a. We know the moment of inertia I to the origin O is sigma I mi Ri square. So calculating the I for each mass, we will get I is equal to m into root 2a whole square plus 2m into root 2a whole square plus m into root 2a whole square plus 2m into root 2a whole square equal to 12ma square. By perpendicular axis theorem, Ix plus Iy should be equal to I, that is 12ma square. And the only possible choice is B. Now problem number 4. Consider a particle of mass m moving with a velocity v. If Tr denotes the relativistic kinetic energy and Tn its non-relativistic approximation, then the value of Tr minus Tn by Tr for v equal to 0.01 C is, the right answer is C. Note that in all the CSR exams, relativistic energy equation problem is a sure question. So let us work out this problem very seriously. So let the relativistic kinetic energy Tr equal to mc square, that is total energy, minus m0 c square, that is rest mass energy. Now we know the equation for mass expansion. So substituting m is equal to m0 divided by root of 1 minus v square by c square, we get m0 c square into 1 minus v square by c square raised to minus 1 by 2 minus 1. Now let us expand 1 minus v square by c square raised to minus 1 by 2 using binomial expansion. So we will get 1 plus half into v square by c square plus minus half into minus 3 by 2 by 2 factorial into v raised to 4 by c raised to 4 plus etc. And subtracting 1, and the solution becomes half m0 v square plus 3 by 8 m0 v raised to 4 by c square. Now non-relativistic kinetic energy is half into m0 v square. So let us find the ratio of Tr minus Tn by Tr. So that is equal to 3 by 8 m0 v raised to 4 by c square divided by half m0 v square. Even though it is non-relativistic one, the denominator approximation would not change the calculation. So we will get 3 by 4 into v square by c square. The answer becomes 7.5 into 10 raised to minus 5. So answer is choice C. Now question number 5. A Hermitian operator O has two normalized eigenstates 1 and 2 with eigenvalues 1 and 2 respectively. The two states u equal to cos theta ket 1 plus sin theta ket 2 and ket b equal to cos phi ket 1 plus sin phi ket 2 are such that bra v o ket v equal to 7 by 4 and uv bracket equal to 0. Which of the following are the possible values of theta and phi? So this is also a very familiar question in quantum mechanics. So answer is, let us find out what is V of V. Given V of V is equal to sin by 4. So we substitute for V, O and V to get the answer. And it is given in the question that when O, the operator, operates on 1 gives 1 eigenvalue, as well as O when operates on 2 gives 2 eigenvalue. So this can be also be useful while substituting. So you can see that V of V equal to bracket open cos phi 1 plus sin phi 2 O into cos phi 1 plus sin phi 2. So it results cos square phi 101 plus sin square phi 202. So that gives cos square phi plus 2 sin square phi. Since the second term 202 will yield an eigenvalue 2. So that is equal to cos square phi plus sin square phi plus sin square phi, that is equal to 1 plus sin square phi, and that answer should be equal to sin by 4. So sin square phi equal to 7 by 4 minus 1. So 3 by 4. So sin phi is equal to root 3 by 2. And it is obviously phi equal to 60 degree, that is pi by 3. Again, taking the second condition uv equal to 0 and substituting the values for u and v, we get cos phi 1 plus sin phi 2 into cos phi 1 plus sin phi 2 equal to cos theta cos phi plus sin theta sin phi equal to 0. So cos theta cos pi by 3 plus sin theta sin pi by 3 equal to 0. 1 by 2 cos theta plus root 3 by 2 sin theta equal to 0, and hence tan theta is equal to minus 1 by root 3. So theta is equal to minus pi by 6. So answer is A. Now coming to the sixth problem. The first order diffraction peak of a crystalline solid occurs at a scattering angle 30 degree, where the diffraction pattern is recorded using an X-ray beam of wavelength 0.15 nanometer. If the error in the measurement and the angle are 0.01 nanometer and 1 degree respectively, then error in calculating the interplanar spacing will be approximately, the answer is A. Note that this is a combination question. A combination question from Bragg's law and error analysis. Bragg's law is 2d sin theta equal to n lambda, and given that n equal to 1, so 2d sin theta is equal to lambda, and theta is equal to 30 degree. So we get interplanar spacing d equal to 0.15. Now according to the conditions in error analysis, delta d by d equal to delta lambda by lambda plus delta theta by theta, since the formula for d is equal to lambda by 2 sin theta. And if theta is small, we can use this approximation. So delta d equal to 0.01 by 0.15 plus 1 by 30 into 0.15 equal to 1.5 into 10 raised to minus 2 nanometer. So this is very close to choice number A rather than choice number C. And you should also remember that we have taken the error in theta for calculation, while we should have taken the error in sin theta calculations. Now problem number 7. The dispersion relation of an electron in a 3-dimensional lattice in tight binding approximation is given by Ek is equal to alpha cos k alpha plus beta cos ky alpha a plus gamma cos kz a, where a is the lattice constant and alpha, beta, gamma are constants with the dimensions of energy. The effective mass tensor at the corner of the first Brillouin zone, pi by a, pi by a, pi by a, is, now the choice is again C. Now this is also a very frequent question, that is the effective mass calculation, which comes in solid state physics. It is found using a formula 1 by m star, where m star is the effective mass, is equal to 1 by h cut square dou square E by dou ki plus dou kj in tensor notation. Now given that Ek or the energy is equal to alpha cos kxa plus beta cos kya plus gamma cos kza, and hence energy is a scalar, let us write the scalar as a matrix, as a diagonal matrix as shown in the figure. So E equal to a diagonal matrix alpha cos kxa, beta cos kya, gamma cos kza. Now differentiating 2 times with respect to k, that is the x component should be differentiated with respect to kx square, kx, y component with respect to ky, and z component with respect to kz, we get dou square E by dou k square is equal to minus alpha square alpha cos kxa minus alpha square beta minus a square beta cos kya minus a square gamma cos kz a. Now let us substitute the value for kx, ky, kz as pi by a, pi by a, pi by a. And we should also note that it results, cos kxa results in cos pi, which yields an answer minus 1. So dou square E by dou k square gives at the point pi by a, pi by a, pi by a yields a square alpha, a square beta, a square gamma diagonal matrix. So 1 by effective mass is actually 1 by h cut square dou square E by dou k square. So in order to find Mij, we should take the inverse of this matrix. So you will get h cut square, and since it is a diagonal matrix, finding an inverse to that matrix is very simple. It will be actually 1 by a square alpha, 1 by a square beta, 1 by a square gamma diagonal matrix. So we will get h cut square by a square into 1 by alpha, 1 by beta, 1 by gamma, which is the solution C. Now coming to question number 8. The electrical quadrupole moment of an odd proton nucleus is equal to 2j minus 1 by 2j plus 1, average value of r square, where j is the total angular momentum. Given r0 is equal to 1.2 femtometer. Now you are asked to calculate the quadrupole moment in barns. Here it is again a combination question of equations such as r is equal to r0 a raised to 1 by 3. The equation for the average value of r square, and to find the j value using shell model. Now first of all, we have to understand that aluminum 27 has 13 protons in it, and that prior knowledge is important to solve this. Now the odd number of nucleons is protons. So using shell model, in order to arrange 13 protons, we should come in a shell 1s half 2, 1p 3 by 2 4, 1p half 2, 1d 5 by 2 5. So j is equal to 5 by 2. Now quadrupole moment is given as 2j minus 1 by 2 into j plus 1 into average value of r square. Now average value of r square is minus 3 by 5 r0 a raised to 1 by 3 all square. So substituting these values, we will get q equal to minus 3 by 5 into 4 by 7 into 3.6 into 3.6 into 10 raised to minus 30 meter. Now we should note that 1 barn is equal to 1 into 10 raised to minus 28 meter square. So you will get q is equal to 0.044 barns. Hence the answer. Now coming to question number 9, we are given 4 reactions, and also some statements are given relating to the reactions 1, 2, 3 and 4. So it is just to check for QBLS. So just study the attributes which we learn in our lecture notes while discussing particle physics. So let us check each one out. Now question number 1. Neutron gives antiproton plus positron plus antineutron. We check for Q. It is correct. Everything is conserved. Charge is conserved. Now we go for baryon number. So you have to learn the baryon number for each particle. So there also baryon number is conserved. And it is said in the question that the choice A says that baryon number is not conserved. That is not true. So choice A is not the correct answer for this question. Now the second question we can see the antiproton plus neutron gives pi minus. Here charge is conserved, baryon number is conserved, lepton number is conserved, and straightness is also conserved. But we know that the proton and antiproton as well as neutron have a very large mass than pi mesons. Pi mesons have only 270 times mass of electron, while neutron have 1800 times mass of electron. Hence, the choice B is a true statement. That is, conservation of mass and energy is violated for this reaction. But let us check further also to confirm that choice B is the answer. So let us take the third one. That is proton plus neutron gives pi plus plus pi 0 plus pi 0. So here we check for Q and B. And we see that baryon number is not conserved. And hence this answer, this interaction is also not possible in any type of interaction, even if it is strong or weak. Just because baryon number should be conserved in any type of reactions. Now coming to the last one, that is proton plus antineutrino gives neutron plus electron. Again we check for Q, B, L and S. We see that the lepton number is not conserved. Lepton number is conserved. Lepton number is conserved. It is said that the choice D, lepton number is not conserved. But here it is very clear that lepton number is conserved and hence choice D is also not the answer. So most appropriately choice B is the answer, and we have also discussed the point why choice B is the answer for the present question. Now coming to the last question in this week's discussion. A thin film of dimension 2 mm cross 2 mm contains 4 into 10 raised to 12 electrons. The magnitude of the Fermi wave vector of the system in the free electron approximation is B, root 2 pi into 10 raised to 7 centimeter raised to minus. Again, let us discuss the answer. Note that this is a very frequent problem since Fermi energy is a topic which comes both in statistical mechanics and solid state physics. So refer my notes in statistical mechanics for doing 3D problems. But here, since we are discussing Fermi energy in detail, let us recollect what is written in my notes. We know the Fermi energy EF is equal to h cut square k square by 2m, where k is the Fermi wave vector. And Fermi energy is the uncertainty energy. Now we know the Heisenberg uncertainty principle, that is delta x, delta y, delta z, delta px, delta py, delta pz equal to h cube. Now the volume can be written as delta v. The momentum volume, let us take it as 4 by 3 pi delta p cube equal to h cube. Here we are considering 3D, isn't it? So delta p cube gives the value 3h cube by 4 pi delta v. Now let us think about the concept of electron density. If n is the electron density, it means n number of electrons occupy unit volume. But electrons are of two natures, that is spin up electrons and spin down electrons. Or in other words, we can say that n by 2 spin up electrons occupy the volume 1 unit. So 1 upspin electron occupy the volume 2 by n. Substituting this value in delta P, we get delta P equal to 3n by 8 pi raised to 1 by 3h. Now Fermi energy is what? Uncertainty energy. That is delta P square by 2m. So substituting that value, we will get h square by 2m into 3n by 8 pi raised to 2 by 3, which is very famous equation, and we have already learned that. Now equating with h cut square k square by 2m, we get k square equal to 4 pi square 3n by 8 pi raised to 2 by 3. Solving, we get k equal to 3 pi square n raised to 1 by 3. This is also a very famous equation for Fermi wavelet. But here we have a 2D problem in hand. So let us proceed in a similar manner because the logic is almost same. We take the Heisenberg uncertainty principle in 2D. So delta x, delta y, delta px, delta py equal to h square. So let us take delta x, delta y as delta e. Delta px, delta py as pi delta p square. So that is equal to h square. So delta p square will be equal to h square by pi delta e. Again, let us argue in the similar manner. If n is the electron density, n number of electrons occupy unit area. That means n by 2 up spin electron occupy unit area. So 1 up spin electron occupy 2 by n area. Substituting delta p square, you will get it as h square n by 2 pi. It is delta p square. So EF is equal to delta p square by 2. Substituting, you will get h square n by 4 pi m, which is equal to h cut square k square by 2m. So we will get k square is equal to n by 2 pi into 4 pi square. So k is equal to 2 pi n raised to 1 by 2. Now given that 4 into 10 raised to 12 electrons are there in 2 by 2 millimeter area. From there we find electron density, but electron density is taken in per unit area. So we will get 10 raised to 14 electrons per centimeter square. Substituting k, you will get it as root 2 pi into 10 raised to 7 centimeter raised to minus. Hence the answer is B. Now, conclusion. We have seen that the problem is getting tougher and tougher, but this type of problems can be solved if you work hard. So one of the hardest decision you will ever face in life is choosing whether to walk away or to try harder. Thank you. We will come back again with week 3 discussions. Thank you.